Hello, welcome to GUM Uncertainty Framework Part 1. I'm Richard Leach, Professor of Metrology and the leader of the course. Okay, so let's look at what we're going to cover today. It's quite a complex subject, uncertainty analysis. There's a lot of little things you need to do, and to be honest, the best way to learn uncertainty analysis is to sit down and do an uncertainty budget. However, there are a bunch of background formulae and principles that you need to understand before you can do that. And hopefully I'm going to get those across to you today. We'll get the very basics across today. And then in the second lecture, we'll cover some more of the complex issues. So today we're going to talk about, again, we're going to talk about systematic and random errors. We talked about that in the last lectures. We're going to cover the mean, standard deviation, the mean. Most of you probably would have covered the statistics while doing this, but it's useful to go over them again, remind you. We're going to look at uncertainty distributions, which are the same as probability distributions and confidence intervals. We'll then look at the concept of the standard uncertainty, how we propagate uncertainties, and if you don't know what the word propagation means, it'll become evident. Then we'll look at three different methods for applying that propagation, which is the direct calculation, using partial derivatives, and using what's called the Monte Carlo method. In the next lecture, we'll talk about multiple variable uncertainty and then how to state the final answer. Okay, so you need to have a little bit of a priori capability to be able to do this course. So I'm going to assume you can all do simple algebra and functions. Also, you need to be able to do partial differentiation of products and quotients and by parts and things like that. So all the relatively simple differential calculus. Partial differentiation is key. Most of the differentiation you'll have to do is partial. Some statistics will help, and also you need to be able to do a bit of programming in MATLAB. So you can get background material for this course is in chapter 8 of this book. I apologise, I can't remember whether it's chapter 8 or 9, but it's pretty obvious because it's called Uncertainty. Most of this course is in fact based on the material in that chapter. There's also this good practice guide published by Stephanie Bell at MPO, and this is free to download, so I encourage you to do it. However, it's a bit simplistic, so it allows you to do a very, very basic uncertainty analysis, but it won't allow you to do anything with products or quotients or multiple variables, etc., which, to be honest, is pretty much what you always come across in practice. The main text on uncertainty analysis is what's called the GUM, and you'll hear me talk about the GUM many times throughout the lecture. So the GUM is the technical title is the Evaluation of Measurement Data Guide to the Expression of Uncertainty in Measurement. And this is a document that was put together for some time now. In 2008 it was first published, but it probably took about 10 years to produce. And it was produced because there wasn't really a framework which people in industry that were doing measurements or academia could apply, that meant that they were all coming out with something they could compare at the end of the day to do uncertainty analysis. There was lots of different methods, lots of different approaches, but nothing harmonized. So the point of this was that it harmonized the approach to uncertainty calculation. What it isn't is rigorous from a mathematical standpoint. There are many holes that a pure mathematician or a pure statistician could pick in the GUM, but at least it means that we're all getting it wrong in the same way to a certain extent, and there's many times when it's just not possible to be rigorous because we either don't have the mathematical infrastructure or that it would be too difficult to apply in an industrial context. So GUM is a simplification, but it's the most widely accepted method that's used throughout the world. There's two editions. The first one is addresses just using uncertainty budgeting, which we'll cover. The second part, or the supplement 1 as it's called, is the extension which allows you to use the Monte Carlo techniques. And then there are discussions at the moment to use what's called a Bayesian framework, which tidies up some of the mathematical problems. There are other documents. There's plenty of documents out there. These 2 I would recommend. There's the Evaluation of Uncertainty of Measurement in Calibration, published by the European Accreditation Group, and NIST, the National Institute of Standards and Technology, which is the National Measurement Institute in the US. This is an excellent guide. I thoroughly recommend this. Also, if you just want to look up a particular point about uncertainty analysis, then just going onto the NIST website and searching is a really good way to find out what you want. So measurement uncertainty, what is it? Well, we said in the first or the first 2 lectures that there is always some uncertainty about a measurement. There's always a margin of doubt about that particular measurement. The questions we need to ask when we do an uncertainty analysis are, how big is that margin? So how do we quantify that margin? And how bad is that doubt? So we're going to try and put some kind of quantification around the margin and the doubt. So every measurement is subject to some uncertainty or some error, as we've said before. So the measurement result is incomplete without a statement of uncertainty. So there's no such thing as, because you don't have a perfect measurement, there's no point in just stating what the measurement result is. You need to understand what that margin of doubt is as well, and you need to quantify that. So really, if you see a measurement result just on its own, it is not complete until it's got that statement of uncertainty. And more to the point here, and I think I talked about this in the first couple of lectures, is that you cannot compare 2 results unless you understand that uncertainty. So when you know the uncertainty in a measurement, then you can judge its fitness for purpose. So, for example, in manufacturing, we might have a tolerance or some kind of design criteria, and you need to be able to match the result to that. And you can't do that. You can't start talking about tolerances until you understand measurement uncertainty. So understanding measurement uncertainty is also the first step to reducing it. So if you have carried out a rigorous uncertainty budget, you'll have a good understanding of where all your sources of uncertainty are coming from, and then you can go back and address them and start using vibration isolation, thermal isolation, and things like that. Good measurement practice can reduce uncertainty. So often, if you've got good guidelines for your measurements and you've optimized your measurement setups and your training for the personnel and things like that, then those good practice can get that uncertainty figure down. So why do we need uncertainty? Why do we need to estimate uncertainty? Notice we always say estimate uncertainty, and that's because it's always a statistical estimation. It's never an exact value. So to know what the uncertainty is in your measurement process, that's pretty obvious. To demonstrate that you have considered it, and this is important, for example, if you're being audited from a quality assurance point of view, or your customer wants to see that you've done it. To know the most important uncertainties so you can work to reduce them. We just discussed that. And to operate within your budget. So, and again, this could, in a manufacturing context, this could go back to a tolerance budget or something like that. And you would then make sure that your measurements are complying with that particular tolerance. So here's the rigorous definition according to the GUM. It's a measurement of the parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurand. So in other words, how much it varies around that, whatever that measurand result is. And there's some notes that go with the GUM definition. The parameter may be, for example, standard deviation, half width, or some other statistic. Uncertainty of the measurement can comprise many components. Pretty much in every case, certainly every case I've ever come with, it always does comprise of many components. And it's understood that the result of the measurement is the best estimate of the value of the measurand, that all components of uncertainty contribute to the dispersion. So where does it come from? Well, it comes from those error sources that we talked about in the first two lectures: biases, drifts, noise, the condition being measured, which may not be stable, the measurement process itself, imported uncertainties. So, for example, if you've got a calibration certificate, say it's a gauge block, and you've got a length calibration with a certain uncertainty associated with that calibration value, then you need to import that value into your uncertainty budget, because you can never be better than the calibration value. Operator skill, sampling issues, the environment, so temperature and air pressure, vibration, things like that. So here's the steps on the path to uncertainty, and we'll go through all of these steps, certainly in both lectures. So step 1, analyze the measurement process and identify the influence quantities. So this is typically your lab book step. So you would sit down with your lab book and analyze your measurement process, maybe using flow diagrams, box diagrams, things like that, and work out what the biggest the influence quantities are. So what is it that's causing things to change? List any simplifying assumptions that you've made which will impact your measurement. Form a mathematical model of the measurement in terms of influence quantities expressed in some kind of optimal form. We'll go through some examples of doing that. Step 4 is evaluate the sensitivity coefficients. That's where your partial differentiation comes in. So now you're going to try and work out how those particular influence quantities affect the measurement results. Evaluate the standard uncertainties and the degrees of freedom of the influence quantities. We'll cover all of this. Determine any correlated components, and we won't get onto that today, but we'll cover that in the next lecture. And calculate the combined and expanded uncertainties and degrees of freedom for the overall process. So that's the final value that you would quote. So 7 steps. So let's talk a little bit about that model. Well, if we think about a very simplistic model, we would say that the true value, the value that we measure, equals whatever the instrument reading is minus the sum of all the errors that you get. So these are the knowable, correctable errors, such as calibration errors, and all the unknown errors, which are effectively the uncertainties. Because even if we apply a correction for a systematic error, there will still be some uncertainty left in that correction. So another way to think about it is that the true value equals the instrument reading plus the known corrections, and then the uncertainties in those known corrections, and the uncertainty that's left behind, the residual uncertainty. So we're going to take a little interlude now and go over some of the statistics that are essential to uncertainty analysis. If you can't do statistics at all, then you can't do uncertainty analysis. It is an essential skill. I was lucky enough to do an A-level in statistics, which has been helpful for my uncertainty analysis I've done as part of my career for many years now. So from repeated measurements, you can calculate a mean. And this is what we usually approximate with the true value with. And we can calculate a standard deviation. And this shows us the spread in the reading. So it tells you something about the uncertainty of your result. So note that more measurements can give you less uncertainty, because you get more information about the thing you're trying to measure, and you can reduce the scatter by a factor of the square root of n. So it's always good to do repeat measurements. You can reduce your uncertainty, and it's diminishing returns. So because it's the square root symbol in there. So the distribution that we use to represent many uncertainties, and it's usually the default distribution if you don't know anything else about your sample, is the normal distribution. So this has a probability density function of f of x equals 1 over sigma root 2 pi e to the minus x minus mu squared over 2 sigma squared. So you may or may not recognize that. It's a simple exponential function, or weighted exponential function, and from that you can calculate what the population mean is. So x is your readings basically, and f of x is the function on those readings. So The sigma is the population mean. Mu is the population mean, and sigma is the population standard deviation. Notice I use the term population there. So this would be for the whole population. If we were talking about human beard length, for example, then we would have to measure every human on the planet to calculate the population mean and the population standard deviation. So typically in practice, we would approximate those with the sample mean and the sample standard deviation, which we'll come across in a bit. But if we've got that exact formula, then we can calculate the mu and the sigma. And there you can see a plot of the probability distribution, and some classic statistics are the probability that the mean is in the interval mean plus or minus 1 sigma, and that's at 68%. So that's one standard deviation, or 1 sigma as it's often called. The probability that the mean is in the interval plus or minus 2 sigma is 95%, and then you could go to 3 sigma would be 98%, etc. So just to look at some of the equations now, we talked about the sample mean. So if you assume you take n measurements of a single valued parameter, and if you only take n, then unless n is the total number of the population, then this will be a sample statistic. So you say n measurements of a single valued parameter, e.g. a displacement or a mass or something like that. A good approximation of the true value is the mean, and the mean is simply calculated by summing all the readings you get and divided by the number of readings. Then the dispersion of the measurements is approximated well by the sample standard deviation, which is the approximation of the population standard deviation, and that is that's often called the root sum of squares. So it's the sum of your individual points minus the mean squared over n minus 1, and then you take the square root of the whole thing. Notice that's n minus 1. If you were calculating sigma would be 1 over n, but we have to reduce basically what's called the degrees of freedom, because we're approximating the population with a sample. So and therefore we've lost some information about the whole population, and we represent that by taking n minus 1 as the quotient. So S and X bar are probably the two equations which you'll use the most in uncertainty analysis. The standard deviation of the mean is another statistic which is very often used in uncertainty analysis. It's sometimes called the standard error of the mean. That's an older term for it. And it's approximated by the standard deviation divided by the square root of the number of readings that you take. And we'll talk about the difference between the two in a minute. So if you take repeated measurements to give a better result, but are not efficient, as we've said, because of the square root in the quotient. And also you need to be careful, because if your measurement is drifting, for example, if the temperature is changing, then you might not be able to represent the measurement as you increase the amount of time that it takes. Also, repeated measurements do not reduce the standard deviation, but they will reduce the standard error of the mean, or standard deviation of the mean. Note that S squared, the square of the standard deviation, is often called the variance. So just to go through the equations, so we've got two ways of representing dispersion. We've got the standard deviation, and we've got the standard deviation of the mean. So which one should we use for uncertainty estimation? And the answer is we use both, and this is easily explained with an example, and I'm going to show you a little YouTube video on this as well. So it depends on the definition of the measurand as to which you use. Most cases you come across it's the standard deviation of the mean, but if the measurand includes that variability, then you have to use the standard deviation. So S is a measure of the variability about the mean, so how your population would vary about the mean, and SM is a measure of the difference between the mean and the true value. So there's a subtle difference between those two. It's subtle but important for you to understand. So I'm going to show you this little video, and I hope it plays without too many adverts.
Hello, and welcome to another Stat Quickie. This time, we're going to talk about the standard deviation versus the standard error. These terms are often confused, so let's clear them up once and for all. I think the easiest way to understand the differences between the standard deviation and the standard error is to look at an example. For the sake of this example, imagine we weighed 5 mice. This is the average, or mean, of the values we measured. This is the standard deviation on both sides of the mean. It quantifies how much the data are spread out. Now imagine we did the exact same experiment, weighed 5 mice, 5 separate times, using different mice each time. This would result in 5 means, or averages, 1 for each set of measurements. We would also have 5 separate standard deviations around the means, 1 for each set of measurements. They quantify how much the measurements are spread around their means. Here's what it would look like if we plotted all 5 means on the same number line. This is the mean of the means, and this is the standard deviation on both sides of the mean of the means. It's a little bit of a tongue twister there. The standard deviation of the means is called the standard error, and that's all there is to it. It's just that simple. Now let's summarize the differences between the standard deviation and the standard error. The standard deviation quantifies the variation within a set of measurements. The standard error quantifies the variation in the means from multiple sets of measurements. The confusing thing is that the standard error can be estimated from a single set of measurements, even though it describes the means from multiple sets. Thus, even if you only have a single set of measurements, you are often given the option to plot the standard error. In almost all cases, you should plot the standard deviation, since graphs are usually intended to describe the data that you measured. For more information on standard errors, check out the StatQuest on standard errors. Also, the StatQuest on...
Okay, so let me shut this down and we can move on. So hopefully, I thought that was a really good video that made things pretty clear. But let's look at an example now from my own field, which is surface texture measurement. So we're measuring a surface that happens to be an additive surface using an optical instrument. It doesn't matter which one. You'll cover all the optical instruments in some of the forthcoming lectures. But for now, we don't care. We're just trying to represent the principles of these two dispersion values. So we measure the surface. So in the first experiment, we measure 5 times in the same place. So we get 5 representations of what you can see on the right there. And we're going to calculate the uncertainty from those 5 measurements. In the second case, we measure over 5 different places. So we've taken 5 independent positions across the surface. There you can see it on the graph. So that's 2 different measurements of that surface. But in the first case, in the case when we take 5 repeat measurements but not spread across the surface, then we can use the standard error of the mean. But in the second case, we need to use the standard deviation. Hopefully that's clear from the video and what we've said so far. Okay, it's important to realise that. So please do spend a bit of time thinking about that, and make sure you understand the difference between those two, because they will give different answers. So we talked a little bit about the normal distribution, or sometimes called the Gaussian distribution, which is probably the most common. The second most common is the rectangular distribution. And this is where basically we know that the measurement, and it's a purely random distribution, this, so we know that the measurement is somewhere between A and B. And a classic example here would be if we had a digital multimeter or a digital meter of some kind, and if we were representing the resolution of some error, then we would just know that it's in the last figure. So we would have a range of two values, but we don't know where it is in between those. It's purely randomly dispersed between 0 and 10, or plus or minus 10 or something like that. So the probability density function of this would be it's 0 everywhere, and then it's somewhere in between B minus A. So you'd represent the probability as 1 over B minus A in this case. So from that we can get the same statistics again. So we can get a mean and a standard deviation. They're not the same as for the normal distribution. So the mean would be the absolute value of A plus B over 2, and the standard deviation will be the square root of B minus A squared over 12. Don't worry about where that's come from and why there's a 12 in there. It's quite easy to calculate from the probability density function just by integrating, but you can just accept that formula. And you'll often see, if you see on the right there, I've just rearranged it so it's 2 root 3 as opposed to 12. You'll often see these 2 root 3s and these 12s floating around in uncertainty budgets, and now you at least know where they come from. The t-distribution is another distribution which is used a lot in uncertainty analysis, and you'll in the second lecture we'll cover how you get the confidence intervals from it. The t-distribution is basically an approximation to the normal distribution. So if we have x independent measurements, x at I from 1 to n is a series of values drawn from the random distribution with normal distribution with mean mu and standard deviation sigma. Then you can let x be an approximation to mu, and the mean is given by the normal formula, the standard deviation by the formula. Then you have this quantity t. Sometimes it's called the student's t value, or just the t value, which is that approximation minus the mean over the standard error of the mean. And this has what's called a t-distribution with n-1 degrees of freedom. So again, don't worry too much about it. It's an approximation of the normal distribution. There are tables. You're rarely going to have to actually calculate it. Normally you would look up in tables, and we'll look at those tables in the second lecture. So for now, you just really need to know that it exists. And there's plenty of other distributions. So there's the normal, the uniform or rectangular, you can get U-shaped distributions, log normal, triangle, quadratic, and there's others. So and these would be used to represent the various uncertainty terms. I would say that in probably 90% of the cases you'll come across, all you'll ever come across is normal and rectangular distributions, but the others exist and they're there to be used. So imagine you've got lots of different types of distributions for your influence quantities, and you need to add those together. In general, if you've got, say, a rectangular and a normal distribution, you can't just add those two up. The statistics are different, so you can't just numerically add them, either just linearly, or you can't add them in quadrature either, which means that it's the sum of squares. So, but even though you can't mathematically add them together, we can rely on this thing called the central limit theorem. And this basically says that when independent random variables are added, their properly normalized sum tends towards a normal distribution. So in other words, as long as you've got them normalized, which means that you're representing them from the same sample or population, then you can add them together if there's a lot of them. So they will all eventually give you a Gaussian distribution. And that, yeah, of course, that's unless one of them completely dominates. So for example, there we've got the rectangular distribution plus a normal distribution, and a few more will tend to eventually give you a normal distribution. So the GUM statistics, you don't really have to use this very much. You can assume that the central limit theorem always applies. In every case I've ever dealt with, it does apply. There are some tests you can do, some statistical tests to see whether you can rely on the central limit theorem or not. I think in most cases you can say that you can. So we talked a little bit about systematic and random errors, but we need to work out how to use them now in uncertainty and budgets. So recall the previous definitions of random and systematic errors. The final uncertainty would be a mix of both types of error. In the GUM, we don't tend to say random and systematic errors. We tend to have two types of methods for evaluating these types of uncertainty or types of error. So that's either type A or type B. Now, there is an almost one-to-one mapping of random onto type A and systematic onto type B, but not quite. And that's why in the GUM you have these types A and type Bs as opposed to the random and systematic errors which we used in the past. So type A and type B are the errors that you get are called standard errors. So let's look at the type A evaluation. Type A evaluation is basically what we do with our random errors. So it's evaluation of a component of the measurement uncertainty by statistical analysis of the measured values obtained under defined measurement conditions. So typically this would be represented by the repeatability, or the precision of the measurement. So if you take repeat measurements and you then calculate a standard deviation or some standard error of the mean, some statistic, then that's what you call a type A evaluation. So examples are standard deviation, standard error of the mean. And you would represent it by a range, but rarely. Type B is everything where you can't find some kind of standard deviation in a simple statistical sense. So it's any other methods. You can express it as a standard deviation, but you don't calculate it in a statistical sense. So you would represent type Bs via rectangular distributions, because you only know that it varies somewhere in a particular range. So the calibration uncertainty of a physical reference specimen, published uncertainty, a known uncertainty from equations or something like that, known uncorrected systematic errors. So all of these, so biases and things like that, all of these are basically type B evaluations. So let's look at the concept of the standard uncertainty, U. So type A, you can either use the standard deviation or you can use the standard deviation in the mean. And we've already been through how you did that, how you choose which of those two to use. So in type B, then typically you'll have something else that you need to do. It could be a resolution on a specification, uncertainty in the calibration, error that's not corrected, estimated temperature influence, those types of things. So typically you can't calculate your standard deviation from a population using statistical analysis. You have to rely on some other method, but you still need to find a standard deviation. So often that's why you use rectangular distribution. You use the equation for the standard deviation of a rectangular distribution. So propagation of uncertainties, let's discuss that. So suppose we have a measured value x, which has a standard deviation s of x. Now we want to know what is the standard deviation s of y if we have a function y equals f of x. So let's do an example. So let's say we're measuring the diameter of a ball using the calipers that we looked at in the last lectures, and we get we measure a value of 24.735 millimeters. Let's take that as the nominal value. So we want to know what a deviation of 0.049 millimeters in D means for the volume. That's what we're trying to find now. Or we want to know the volume, V equals y of x, that's our function, and if that was in terms of diameter, it would be pi d cubed over 6. I hope you can see where that comes from. And it's standard deviation in the volume due to the standard deviation in SD. That's what we're going to look at. So here's our measurements. We've taken 5 measurements. So our individual terms are xi, then xi minus x bar is where we've just normalized them by taking the mean away, and then we've got that squared term as well, because that's what's used in the standard deviation calculation. So the mean is that value, that's the value we were just talking about, 24.735 millimeters, and the standard deviation using that equation comes to 0.049 millimeters. So let's work out how we propagate the uncertainty. So how do we get an uncertainty value using our equation for volume? Well, there's multiple ways of doing this, but the usual way you would do it is you'd look at the value of the function at the normal value plus the uncertainty, and then take away the value of the normal value. So with our volume, we've got the volume equals pi d cubed over 6, which is pi with our d value in there, which comes to 7923 millimeters cubed. So let's calculate that difference there, so the direct calculation of the standard deviation. So the uncertainty in the volume equals the uncertainty at the displacement plus the small error minus the uncertainty in the volume at that displacement. And there we plug the values in, and you're going to get 47 millimeters cubed. Okay, so that's one way to calculate the uncertainty in that volume measurement. Just a quick interlude. So we need to understand the Taylor expansion, because we're going to use it in the derivative method. So if we've got some value where that epsilon, which is a lot smaller than the measured value, then the Taylor expansion tells us that the function on x plus that small value equals the value of the function plus epsilon times the partial derivative of the function with respect to x plus epsilon squared over 2 factorial times the second derivative plus epsilon cubed over 3 factorial times the third derivative, etc., etc. Usually we cut off at in most calculations we can cut off at the second order term. So just bear that in mind at the moment, that we're going to use the Taylor expansion. When you see these types of expansions going on, then you'll realize where it comes from. So method 2 uses derivatives to calculate the uncertainty. So again, we've got that f of x plus mu of x, so the value plus the uncertainty equals, and again we've done the Taylor expansion there, so it's f of x plus df of x by dx times u of x, which is the epsilon in that case, plus the second order term. So let's just pull that apart. So if we want the uncertainty in y, then we take the difference between the function with the uncertainty included minus the straight function. That's the first method we went through. But that's the same if we do the Taylor expansion of that the first term there. Then and we just use the first order term. Then it's f of x plus df of x by dx times u of x minus f of x. And of course that just cancels the two f of x's there and gives us that partial derivative. And that, we call that, often we say that's the sensitivity, because it's how sensitive, it's the gradient of f of x with x. So it's telling us how that changes for a given change in x, how the function actually changes itself. So this is where many times in uncertainty analysis you'll come across this derivative times the uncertainty term. And notice that it's an approximation, it's not an exact derivation. We will look at the exact derivation in the next lecture, but this approximation is applied and almost universally used. So this is another way of calculating it. So let's go through our example, same numbers. So the uncertainty is the first derivative of the volume with respect to the displacement measurement times the uncertainty in the displacement, which equals, in this case, d by dd of pi d cubed over 6 times u of d equals 3 pi d squared over 6 times u of d. I hope you can see where that comes from just by partially differentiating that, which equals 3v over d u of d, which gives us a relatively interesting result because it means that the uncertainty in the volume, or the relative uncertainty in the volume, equals 3 times the relative uncertainty in the displacement. So we only really need to calculate the uncertainty in the displacement and it automatically gives us the uncertainty in the volume. And I guess that's sort of intuitive. Let's plug the numbers in. This means the relative deviation in V is 3 times that in D. So from our measurement values, let's plug those in and we basically get the same value. So if you remember, the value previously was 47 millimeters cubed, and that's what we get. So method 1 and method 2 are thankfully agreeing, even though we've made the simplifying approximation that we're only using the first order term of the Taylor expansion. So propagation of uncertainties, let's look at some useful derivatives to know. So let's say that the relationship between f and x is just a constant term. Well, then nothing changes because clearly the partial derivative just cancels the constant. If it's c times x, then it gives us then the relative measurement has changed. That's exactly what we had in the last example. If it's c to the x to the power of c, then it's the relative uncertainty multiplied by that the power. If it's a log, if it's exponentiation, then you get lots of different relationships, and of course you could do sine and cosine and things like that, but these ones you get used to eventually, and they allow you to make some simplifying assumptions when you're doing your calculations by hand. So the third method is the GUM supplement 1, which is to use the Monte Carlo approach. So what's Monte Carlo? What do we mean by Monte Carlo? So it's basically considered the most correct method to do things. It's often the only method that you can apply because you don't have those simple equations which links things together. So it gives little insight, doesn't really tell you what's going on, whereas the budgeting method allows you to find sensitivity coefficients, it allows you to find what all the various influence factors are. This one doesn't really tell us much about what's going on, it just gives us an answer. Can be applied without much insight, so that's the opposite, is that you don't need that insight. It's difficult to check whether you're getting the right answer. If possible, you can use method 1 and 2, but often you don't have that ability. So you have to trust it to a certain extent, trust the process, as they say. It can handle very complex measurement sequences. So it really doesn't matter how complex it is. I mean, an example would be you'll talk about coordinate measurements, and certainly surface measurements are so complicated in terms of uncertainty analysis that you can only ever think of using a Monte Carlo approach. It gives slightly different results. So if you run a Monte Carlo simulation and you get a particular result, run it again, you're going to get a slightly different result. But usually that's a very small factor and can be taken into account in the final result. So basically what you do with the Monte Carlo method is you know what your various influence factors are, and you propagate, so you have a distribution of the input values, and then you run your Monte Carlo simulation, and that gives you on your model equation, and that gives you a distribution of output values. So in go the various distribution, doesn't matter what they are. You can definitely say that the central limit theorem applies when you apply Monte Carlo, and that gives you an output distribution. It doesn't care what those input distributions are. So the input values, the chi of I, let's say that they are the x, the original value, plus the uncertainty in x times some random number. That's what we're going to do. We're going to randomly sample this. So typically we'd set Zi, the random number, is between has a mean of 0 and a standard deviation of 1. So if we're doing this in MATLAB, we can get a Gaussian distributed random number with s equals with a standard deviation of 1. We can use the function rand n, or a rectangular distribution between 0 and 1 is just rand, and make the mean 0, s equal 1. You can say that z equals r minus 0.5 times 2 over root 3. So let's try it for our particular example. So we know that the diameter is 24.735 plus that standard deviation times r, the random number. So we set our random number. So in MATLAB, you would do that by multiplying it by our Gaussian distribution, and you're going to do 1,000 simulations. That's what that second parameter is. So v equals pi times d cubed over 6, the volume calculation, the mean you've got there, and the standard deviation. So let's see what we get. So the Monte Carlo simulation, we run it 200 times, so vary in that random variable r 200 times, and it comes out with the value that we got on the right there, 47. So again, it's spot on, giving us the same value as the method 1 and method 2. And I've now done it for 1 million simulations, and that's probably more normal with Monte Carlo. And again, you can't see any difference between the two values. It's difficult to say whether you should run this 200 times or 1 million times. Most people say 1 million is the smallest number that's required, but I'm not necessarily going to agree with that. So how many simulations are needed? Well, yeah, statistician's going to tell you 1 million or more. The measurement technician who's got to take those measurements, if he's going to actually, will tell you that he never takes more than, or he or she never takes more than 20. So you never really, although Monte Carlo is simulating reality, it's clearly, because we can do all these calculations, we use a high value. You can use this figure if you want, which says that if the standard deviation divided by root 2n minus 2 is within 5% of your s, then you can use 200 simulations. Means within 1%, then you can use 5,000. But to be honest, in the particular case that we were just going through, and with modern computers, doing 1 million simulations really doesn't take that much time. Okay, so what have you learned today? Again, Monte Carlo, it's a tough thing to teach without actually getting you to do an example. But you can do the examples that I gave you, and if you want me to give you some more examples to do, I can do that. So just contact me. We've gone over what systematic and random errors are. We went through the basic statistics. We've looked at the probability or uncertainty distributions, and we did a little bit about confidence intervals. We'll do more about that in the next lecture and how they're applied in uncertainty analysis. We went through the concept of the standard uncertainty. We looked at how you do the propagation of the uncertainties, and we looked at the direct calculation method. We looked at the derivatives method based on the Taylor expansion, and we looked at the simulation method, which is the Monte Carlo method. So in the next lecture, we'll cover multiple variable uncertainties. So how can we do it if we've got lots of a very complex function, and then we'll look at how we take that standard uncertainty that we calculate and how we turn that into a final result for our manufacturing or whatever we're trying to calculate the uncertainty for. Okay, thank you very much.